types of evolution. We're going to talk today about convergent evolution and then also divergent evolution. So when things converge, they're all coming to the same place from different areas. And so that's what's going on with this too. So we talked about these examples before, although I'm showing them now in a skull. This is, well, this is the wolf, the gray wolf, and this is the skull of that marsupial wolf that's not really a wolf, but looks so much like it. And so these are examples of convergent evolution, when organisms look the same because they have a similar function, not because they have a common ancestor that looked anything like that. So species exposed to the same selective pressures in different parts of the world tend to develop the same adaptations, even though they may be completely unrelated. So I'm more closely related to this wolf than that wolf is to that wolf, if you want to call it that. But they have much more similar adaptations, so they end up looking the same. So these would be analogous structures. So with convergent evolution, you end up getting analogous structures. So that these creatures have 4 limbs, arms and legs, okay, well that would be homologous, I guess, because they came from a 4-limbed creature, but so did bats and squirrels and kangaroos. But they don't have the same faces because they came from a common ancestor with the same face. They have it because they were exposed to the same selective pressures, so they both had to have eyes in the front of their heads and big canine teeth. So the placental wolf and the marsupial thylacine. Tasmanian wolf. Here's another example of fish, whales, and penguins. So fish are fish, and whales are mammals, and penguins are birds. So these are more closely related to, a swan or a sparrow than they are to either of these. And the mammals, the whales, are more closely related to you and to squirrels than they are to these. And the fish are more closely related to fish. So you could easily see someone mistaking this creature for a fish because it looks so much like a fish, but it's not. These all had the same selective pressures. They had to swim through water, and so they had to be streamlined. And so they had to have some kind of appendage on their sides to help stabilize them. And they had to be really streamlined. And so this is, again, convergent evolution, and they have analogous structures. The opposite would be divergent evolution. That's when things start in one place and then end up being different. And that's because they had a common ancestor, but they're exposed to different selective pressures. So populations of species that are separated and evolve under different selective pressures, they end up developing different adaptations as they diverge. So these are different forms of, I don't know if I want to say they're all elephants, but some form of something related to an elephant. So they all have a common ancestor, yet they ended up getting different selective pressures, so they evolved a little bit differently. So here's the ancestral species, and then this is a common ancestor to all 3. Here's the present day, I don't know, is this the African elephant, I guess, and the Indian elephant maybe? And then this is the mammoth that's now extinct. And so the elephants didn't evolve from each other or from the mammal, but they all evolved from this common ancestor. And that they separated out, that's called divergent. They divided, if you will, divergent evolution. So these organisms would have homologous structures. These are structures that are similar because they come from a common ancestor. Even if they don't look the same, there's something similar about them. So maybe the trunk, they all had a trunk. They all have these fairly big ears on the side of their heads. Some of them got much bigger. They all have this little tail. They're usually geographically separated so that there's a barrier to the mixing of genes. And so here's an example of divergent evolution. These are the finches that we talked about. One of them is on the mainland, and the others are all on the different islands of the Galapagos. And so this was the species that was the common ancestor, and it gave rise to all these different species, some of them that are better at picking bugs, maybe out of a cactus or something, and some that are better at breaking seeds or, big seeds. Adaptive radiation, or adaptive radiation. This is the evolution of many diversely adapted species from a common ancestor, and that's called adaptive radiation. So this happens when you have one ancestral species and its populations, or a bunch of them, go to a bunch of new habitats. So if you have a bunch of new habitats opening up, and the habitats are different from each other, and this population gets geographically separated from that one and that one and that one, then eventually you can get enough differences that you have very, very different organisms. And so this tends to happen if you all of a sudden have some area that's totally new. So let's say there's a big asteroid that hits the Earth and it kills off all these big dinosaurs. Well, you've got all these teeny little mammals running around, and over time, now that the dinosaurs are dead, there's more niches, if you will. There's more places for these other organisms to live. And so maybe one that maybe there's a lot of like bigger animals to eat, and so maybe one of these will end up getting bigger. So that's the kind of thing we're looking at. And that's it.